So in this lecture, we would learn about the topic of state reduction. So mm, what is a state reduction actually? If you see this state table, there are so many states you can list down. So given a problem, you have identified so many states, and you have drawn up the state table or the state diagram, whatever. Now it might so happen that some of the states are redundant in nature. Okay, some of the states are redundant in nature. So in that case, they have to be removed. So that is the state reduction method. So let us go about the steps first. What is basically the state reduction method? So uh, sometimes we would need to reduce the number of states from the either the state table or the state machine diagram, so that we come to a economic circuit design. Okay, the state reduction is needed for economic circuit design, and these are the states which are considered duplicate states. So which states we are reducing? Those which we will consider as duplicate states. What are those duplicate states? Those states whose next state and output are same for a given set of input. So whenever one set of input is coming for a present state, we observe that the next state and the output, both combination, next state and output combination of that particular present state is same as another state, then these will be treated as duplicate states. So only one of the duplicate states will be considered and the others will be omitted as redundant. Let us go about the example, then you will understand better. So this is the state reduction method. Let us see what is happening here. So without state reduction, this is how the state diagram looks like. Without the state reduction, this is the state diagram, and you can observe that this is a Mealy diagram. This is a Mealy diagram. So the output depends on the input actually. Now you observe that which of the states are duplicate states. So to identify duplicate states, what we have to do? We have to see that the next state and the output combination is same. The next state and the output combination is same. Okay, so in which states the next state and output combination are same? So let us see. I think this one, you see, notice the next state is AF and output is 0 1 for your inputs 0 and 1. So similarly here also you see AF 0 1. I think these two are the duplicate states. So one of these states you can remove. So when you have crossed out the state G, so you could have crossed out the state E also, but in this example we have crossed out the state G. So when we have crossed out G, we should replace G with E. So there are other instances in the state table where G is occurring. So like you see in this place, G is there. So in place of this G, we should write E. So this is the next step. So you see we have changed G to E. So when you have changed G to E, then we should check if further reduction is possible. We should not reduce only once and stop. We should always check if further reduction is possible. Here you can see that as we have changed G to E, I get this state D and F as duplicate states, because the next state and the output combination, you see, becomes same. So F we also cross off. So when we cross off F, we have to replace the F with D, because F and D are the duplicate ones. So F has to be replaced with D. This is what we are doing. Now again we check whether we have duplicate states or not. So we don't have any further duplicate states. So it is a common confusion now that one might suppose that C and E are duplicate states because the next states are same. The next state combination, you see, the next state is A for u equals to 0, D for u equals to 1, and in E, A for u equals to 0, D for u equals to 1. Next state is same, but the outputs are different. In C, both the outputs are 0, in E, the outputs are 0 and 1 for input 0 and 1. Hence, C and E are not duplicate states. So please bear this in mind that both the next state and output has to be same if we have to call some set of states as duplicate states. So there is no further reduction. Okay, there is no further reduction, and we have a reduced state table with only 5 states. Instead of 7 number of states, we have come to 5 number of states. So this is the reduced state table, and you see the reduced state diagram will immediately follow. So this is the state reduction method. Another state reduction, let us see. This is for a mood diagram. We are seeing for a mood diagram. So here also you can see A, B, C, D, E, F, G, 7 states are there, and as per the state table you can draw up the mood diagram also by noting what is the next state and what is the output. But now we have to do the state reduction. Okay, the state reduction does not actually need the state diagram. It is just for representation we have done. State reduction can be done directly from the state table. So we have to only note the next state and the output combination. So where are they similar? So I can see that this A and C, here the next state and the output combination, you see they are same. I cannot observe anything else here and think yes. So the C has been struck off, and hence we have to replace C with A. Wherever we have C, we have to replace with A. So we have replaced with A, you see, in the second line we have replaced with A. But now again we have to see whether we have further state reduction possible or not. So you can see, you can observe that B and E now becomes duplicate state because the next states are AD and the output is 1. So the E is now struck off. So when E is struck off, we have to replace E with B, and that we are doing here. E with B we have replaced, and we don't have any further state reduction. So this is C, and C is replaced with A, E is replaced with B. So this is the state table now, and then we can reduce it. So the states C and E has vanished. C and E has vanished. So A, B, D, F, G. So there are 5 states again. Now you can rename the states also. That is not a big deal. But the thing is that there were 2 redundant states which we have been able to reduce. So now we can again draw up the state diagram. So this actually simplifies your problem a lot, and sometimes you will see that you can also reduce the number of flip-flops required. So when that is the case, then it is also becoming an economical circuit. Okay. So here we come to the end, but one short thing I must tell you, which I have not given in the slide. So this is the condition. So what we have done is state reduction by identifying duplicate states. But now you might ask this question, which is a very valid question, that when you have these 5 states, to build a system which has 5 states, how many flip-flops you will need? You will need 3 flip-flops, because with 2 flip-flops you can represent 4 states. Whenever you are going to the 5th state, you have to go to 3 flip-flops, but 3 flip-flops will have 2 to the power of 3 equals to 8 total states available in it. Out of those 8 available states, we have only 5 states which we are required to build the system. So what about the remaining 3 states? These 3 states will be there in the system, but you can say that if I start from the initial state, suppose my A is the initial state which I take as 0 0 0, then B, suppose this I take as 0 0 1, this I take as 0 1 0 0 1 1 1 0 0, and if I start from A, there is no possibility that I will ever leave any of these 5 states. There is no possibility because this is how the system behaves. This is the system dynamics. There is no possibility that I will ever be in any of the states other than these 5 states. However, we have to take a precaution, because sometimes during starting or during some mal operation, whatever, it might so happen that we land upon these states which are not used by the system. These states are not proper system states, right? So these are called the redundant states. Redundant states. What to do with the redundant state? So if you ever land upon a redundant state for any operation, due to any operation, if you ever land upon redundant states, then you have to define where you should go if you have landed upon a redundant state. Usually we assign a particular state among the available 5 states as the initial state. Suppose we assign A as the initial state. Normally we define that whenever we come across redundant states, then it should go to the state A in the next clock cycle. So whatever be the input, it doesn't matter, it should go to A. So in this way you complete the state table then, and after that you solve for the next state equations and form the circuit. Output in the redundant state, you should not give any output, so this is also 0. So in this way you complete the state table, then you formulate the next state and the output equations and draw up the sequential circuit. So what are the steps? The first step is of course to form the complete state table as you understand. So that has been covered in the previous lecture. We have solved different examples. So you have come to a state table. You have come to a state table. From that you have to do state reduction. After you have come to the state table, you see whether there is a possibility of state reduction. Then you get reduced state table. From that you have to take care of the redundant states, if there are redundant states. And then you form the next state and output equations. This is the way to go. I hope this is clear. So this, again I mentioned, this choice of the state in which you should land upon if you have come across a redundant state, this choice is entirely your own choice. But usually we fix a initial state or a reset state, initial or a reset state, and in that state we go whenever we come to some of the redundant states. Normally this will not happen, but if it happens, then the circuit should have a provision to go to the reset or the initial state. If you don't include this provision, then you will not draw up a circuit which is able to do so. So this has to be included. So this is what I needed to discuss in this lecture, and in the next lecture I will cover the one important, which is the last part of our course, which is the conversion between Moore and Milli systems. We have already observed that a particular problem could be designed as a Milli circuit as well as a Moore circuit. We did this in the last lecture. That means there must be a conversion which is possible between Moore and Milli circuit. That will be taken up in the next lecture. Thank you for your attention.